All right. Hi, everyone. Thank you for joining us today. We're really excited to have you all with us here as we jump into session 1 of the Tovi mini-series. I'm Abby Brooke, a product marketing manager at LI-COR, and today I'm going to help serve as moderator for the session. So just a few things before we get started. If you would like to follow along during the session, please have your Tovi software and datasets ready to go. If you have 2 monitors, we found that that might work best to follow along, but if not, don't worry, you can still do it on a single monitor and you can resize the Zoom application as we go along. And as a reminder, we are going to be recording today's session and posting it online in a few days. So if you want to rewatch it at any time for a refresher, you'll be able to do that. And as soon as we have it online, we will let you know. So in addition to me, we also have the following presenters and panelists with us today. We've got Dave Johnson, who's a Senior Technical Product Manager. We also have Israel Begashaw and James Kathalenko, who are Senior Application Scientists at LI-COR. So today we're going to start out with Dave looking into the files created in EddyPro and describing how to create a project in Tovi with those files and data from weather stations near your site. After that, we're going to hand it over to Israel. And he's going to discuss quality indicators from EddyPro and Tovi and show you how you can perform QC on your data sets with Tovi. During today's session, we will be available for questions. So if you have questions, please use the Q&A tool in the Zoom application. I've got it shown here on the slide. And we're going to do our best to answer your questions throughout the session. We do have quite a few attendees today, which is really exciting. So if we don't get all the questions answered, we will follow up after the event. Okay, with that, I think we're ready to go ahead and get started. So Dave, I'm going to go ahead and hand it over to you.
Okay, thank you. Okay, are you able to see my screen? Okay, let's go ahead and get started. Welcome everyone, and happy Earth Day to everybody out there. And this first session, as Abby talked about, is going to describe how to take eddy covariance data from EddyPro and import it into Tovi. So we're going to show some pretty cool tools later on how to, for example, bring in eddy covariance weather station data and synchronize it with your eddy covariance data. And again, Israel is going to talk about our quality screening tool and how to use flags and do some U-star filtering and do things like that. So we're excited to show you how to do that. Again, as Abby said, there's some sample data in the link in the email that you got in the invite. So go ahead and make sure you have that ready when we get to that portion of the presentation. You can also use your own data, and we're going to put some tips in the chat window. So if you want to use some of your own data to follow along, you can go ahead and look at those tips and have your data ready for when we get started. So I'm going to do a short walkthrough to make sure everyone has the data and getting prepared for importing it into Tovi. So as researchers and scientists, you often have interesting questions that you're trying to ask. For example, is your ecosystem a sink or a source? What's the evapotranspiration rates from your field site? Are there leaks of methane coming from the landfill? And you want to quickly get to the answers. And with those answers, you can start writing your publications and secure, say, grant funding for future research. Now, in between those two sections, you have 3 stages of data processing, where you're working with data from data collection, processing the data, and then analyzing the data. And we'll have a quick background of what do we mean when we say raw data collection. So typically in eddy covariance system, you have 2 types of data sets. You have fast data, which we also call the raw flux data, and you have slow data, which is the biological and meteorological data. So our fast data usually is high-speed measurements of the wind speed and direction and the gas concentrations. And normally you're measuring anywhere between 5, 10, or 20 samples per second. Now this is what we call the flux data. Now the slower measurements that are usually made at about 1 time per second or even once per minute are the biological data and the meteorological data, and we call those the biomet data. Now eddy covariance systems, they generate a lot of data. For example, if you're measuring at about 10 times per second, you're going to have over 300 million records over the course of a year from your system. So that makes it really important to understand how you're going to manage and store this data and collect it. Now there's 3 options that primarily people use for an eddy covariance system. This first one I'll talk about is if you have a LI-COR centered eddy covariance station in which you're having all your flux data and biomet data collected and stored in what we call a GHG file. And these files are bundled, zipped, and compressed. And if we have a closer look at those, on the left-hand side, you can see that inside a GHG file bundle, you have those 4 different files that we just talked about. And on the right-hand side, you can see a little description of what each of those files contain. So you have your flux data, which is the gas concentrations in the wind. And then you have metadata about that flux data. For example, the measurement height, the canopy height, your latitude and longitude of your site. Then you have the low frequency data, which is the biomet data, like your air temperature, soil moisture, precipitation, things like that. And then you also have a metadata for the biomet data. So that's describing the variable names, the units you're using, things like that. So what's really cool about this concept is that your metadata and your raw data are always packaged together. So say someone new comes in the lab, say 5 years from now, they know exactly what information was used to collect the data. And it's not going to be lost in some kind of a laboratory notebook or something like that. So if we come back to our data management options, another frequently used system uses a combination of, for example, LI-COR system collecting the flux data, but then using something like a Campbell Scientific data logger to collect the biomet variables. And so if you're in this kind of a situation, you'll have 2 of those CSV files that are bundled in your GHG system. Then the third option that you'll also see a lot of researchers doing is having all your eddy covariance data and your biomet data collected and stored on a logger. And that's typically done in the form of TOB1 files, which are binary files. And those 2 files could be separate or they could be combined into a single file. So now let's shift gears a little bit and talk about the data processing. So as you take your raw data and compute fluxes, you go through a process of doing different algorithms, corrections, and processes where you eliminate errors so that you can get accurate flux measurements from your site. This is just a sample of some of those things that are done. And over the past decades, the eddy covariance community has worked through a processing chain of how to get from your raw data down to your computed fluxes. And you can see how that's typically done here in this flowchart. Now, how to do that? There are several options available for processing your data. A company like LI-COR, ourselves, make a software package called EddyPro. And a company like Campbell Scientific has a package called EasyFlux, which is actually based off a previous version of EddyPro. Then there's people who prefer to use programs like MATLAB or R to do scripts and process their data that way. And some of you may be familiar with packages that are put together by various institutions, and you can see some of them listed here on the slide. So first, we'll talk about EddyPro. Now, LI-COR collaborated with a group that was led out of the University of Tuscia in Italy, and along with a lot of other scientists around the world. And through this collaboration, an open source software was developed and maintained by LI-COR. And if you're not familiar with it, basically you're computing high quality gas and energy fluxes using the eddy covariance method for this. Now, EddyPro has been developed and supported for over 9 years now. And as such, it's become kind of the standard software that a lot of the Flux networks use for processing their data, such as ICOS, Ameriflux, and some networks in China. If you are not familiar with EddyPro, you can see there's a link there on the page where you can go and download that software for free. Now, for those of you that are familiar with EddyPro, there's a new version 7 that you may not be aware of. This came out this last winter. One of the main features in there is a new output file called the FluxNet output. Now this, the content of this file and the format was actually designed with the ICOS, Ameriflux, OSFlux, and FluxNet groups. And the output of this file is ready for direct submission into the latest databases in the Ameriflux and FluxNet that they maintain. This new file has a lot more variables and statistics in it. In addition, all the fluxes, the metadata biomet are combined into a single file. There's some other new features in there that you could find interesting. For example, being able to filter your raw data based on instantaneous wind direction. Now, there's also the possibility to take EddyPro and automate how it computes your fluxes. And you can actually do this on site and in real time. This is a SmartFlex device that accompanies a lot of LI-COR systems. But basically, EddyPro is the processing engine. And this EddyPro that is in the SmartFlex device is the exact same one that's on the desktop. So if you compute fluxes, you have all the corrections and processing options that you normally would on your computer. So now that we've talked about that, we want to examine, based on the system you have, and as you researchers and scientists out there have one of these 3 options, is what you can do to process your data. So as we talked about with the LI-COR and having the GHG files, you can have your fluxes automatically processed, or you can bring the data into your computer, desktop, and run EddyPro with a few clicks. It's fairly semi-automated. Now, if you have one of these mixed systems, you can also run that data through EddyPro. Because the LI-COR system has those GHG flux data, you can either run it through with the biomet, which is the preferred method, or you could also process that data without the biomet if you want to do that as well. Now, with this third option, there's also the ability to take that data, those TLB1 files, and put them through EddyPro, but it's not quite as automated and easy to do, and you actually have to do a little bit of file description to get that to work. But after you get that set up, you can go ahead and do that. And of course, there's always the data processing pathway of using something like a logger program, EddyRe, MATLAB, or something like that. So now that you've processed your data, you're left with about 17,500 records, and they're now split up into 30-minute files. So now what you need to do is take this data and begin an analysis on it. And that's where we move into this third phase. And we're going to spend most of the time talking about that now. So what do you do in the post-processing steps? Typically, you'll do things like quality control of your data. You can gap fill your meteorological data. You can average replicated measurements. You can compute, detect, and filter based on the friction velocity, or what's known as U star. You can gap fill and partition your fluxes. You can investigate the energy balance closure at your site, and you can also do some footprint modeling as well. So LI-COR looked into figuring out if there's the potential to develop a software that can do some of these things. And we wanted to do so like we did with EddyPro, where we collaborate with the community. We want to try and assist in furthering scientific discovery. And as researchers and scientists such as yourself come up with new processes or algorithms, we can help distribute that to a larger community to get that work cited. So when we thought about developing a software, we wanted to try to make it easy to use. And that included putting everything, all these different tools that are out there, into a single platform, creating a very nice user interface that's highly visual. The software has to be robust. built and tested by software engineers. It needs to be backed by our scientific staff, have good documentation. And what's become really important lately is the ability to reproduce what you're doing and being transparent, knowing what you're doing and each along the steps, and being able to document and cite the work that you've done. And so with that, LI-COR was moved forward with the development of Tovi, which is this data analysis software we're going to be spending some time with in this next session. So the development began about 3 years ago, and the first collaboration began with the OSFLEX group, in particular with Peter Isaac there, and in which we implemented QC screening tools and gap filling of meteorological data. We then did some collaboration with the ICOS, Ameriflex, and Euroflex groups to implement some other tools like the U-star detection, and also the gap filling and partitioning of your fluxes. We also did some work with some individual scientists on some of the other tools, including Natasha Kloon and Matthias Mauder. So we're going to get ready to start doing this importing of data into Tovi. Now what Tovi needs for operating all the tools inside there are basically these 4 files which you see listed on the screen. Now the first 3 are provided in the EddyPro outputs. So if you've run EddyPro and you've included the biomet data, those 3 files will be in there. They're also going to be seen in the data that you downloaded in the link in the email. Now if you don't have biomet data, for example you ran EddyPro without it, there are some modifications you can do to the files, and again those descriptions of how to do that are available in that chat window. Now, for those of you that are going to follow along with your own data, I just want to talk about this real quickly. That metadata file that isn't in the EddyPro output is fairly easy to obtain. What you will want to do is go to your raw data, grab any of those GHG file bundles. And what you can do is change the file extension to a .zip. After you do that, you can simply right-click, extract all, and you'll see those 4 files that are in there. One of them will be the .metadata file. And what you can do is then copy and paste this file, move it into where your EddyPro outputs, and then you can find it easy when we go through the importing process. Now, if you need to look at this a little bit longer, again, you can look in the chat window for some instructions on how to do this. So now, as we look at our systems as researchers and how you're set up, how you're processing your data, these are the types of files and what you need to do for getting them imported to Tovi. So obviously with the SmartFlex system and using EddyPro desktop, you're going to have the files needed to go directly into Tovi. Now if you have one of these mixed systems and you have processed your data with the biomet and EddyPro, you're going to have all the files you need. You'll have the metadata file and the biomet file. Now if for some reason you opted out of processing your data with the biomet file, you can see you're going to be missing that biomet data. Now those files are needed for the data that's used for a lot of the tools, those drivers to help run the models. And so again, you'll want to look in the chat window for how to create those biomet files. Finally, if you have this third system where you have all your data collected and processed using like a logger-based system, you can also, as we talked about, run that through EddyPro to desktop and get some outputs. You want to make sure that you do process it with biomet files if you're going to do that. Now, if you've done something like a MATLAB program or have a logger program where the fluxes are EddyRE, those files are not going to be ready to format directly into Tovi and will need some modifications if you want to try to do that. And so with that, we're ready to enter into the Tovi software. So everyone can now open Tovi if they haven't already. And what you'll see, now I have a lot of different sites already created from doing some past work and helping other scientists and users create sites. But for those of you that are new, you will probably just see this one green box here that says to create new site. Okay, you can also have a menu over here that expands and closes, which works kind of like a tree. So you can quickly jump to a particular analysis. So let's go ahead and set one up together. Again, you can use the data that we've provided in the link, or you can use your own data. So we're going to use the data that we provided, and the data that was collected comes from our LI-COR environmental research system. And we have that located at LI-COR, and I'm going to use this acronym here. Now it's fairly simple to do to upload these files. In this bar here, we simply click the Add Files. And what you'll want to do now is navigate in your system to find the data that you downloaded. Now, for us, you're going to find it in one of these folders. I believe the data is called the LIRS Nebraska 1-year data. Now, if you've processed your own data, you can locate that in your EddyPro outputs. So if I go ahead and click here, you can see I'll have these available files. Now, the two that we're going to upload at this point and import is the biomet file and the full output file, okay? So you're just gonna grab these two files at this point. Now, if you have SmartFlux files, you can grab all of those. Again, you have one for every day of the year, and you can just simply select all of them and open them. But for those of you that have run EddyPro, you'll have these two files, and we click Open here, and you can see they'll show up down here. Now we move to the second stage here. This node here is called our site information. Now our site information is where we're going to pull in those other two files that we talked about, the metadata file and the EddyPro project file. The metadata contains all that information about your fluxes. The EddyPro file includes a lot of the processing steps that you did along the way to process your data. So let's go ahead and add those now. If you click this Add Metadata File, now you'll see this file here called lirs.metadata. Again, if you did do this if you are following along with your own data set, this is the file that you're going to have to get from inside the GHG file. And by expanding that out, you can grab one of those metadata files and import that. But for those using the data that that we provided, go ahead and select this one here. What you'll notice is a lot of these fields become populated with that metadata, including the latitude and longitude. And so you can see that your site is dropped on a map. And if you have the correct latitude and longitude, it will show up there. Now let's go ahead and add the EddyPro project file. If you click there, again, you will find that .EddyPro file also inside the folder that we provided that data for. If you processed your data using EddyPro, that'll be in the output folder automatically. Okay, so now what you can see is we have all the information populated. And before we go on to the next step, it's important here that we lock the location. Okay, so if for some reason you need to change the latitude and longitude, they're incorrect, or you don't have that information, you're going to want to enter that before you proceed any further. So let's go ahead and click Lock Location, and we get a simple message that says, are you sure you want to do this? This information is used especially in the footprint tool and for doing various exercises throughout the software. So we hit Continue there. And that should have our location locked. And now we can move to this third node here called External Data. So everyone can go ahead and click there. Now what you'll see is, again, a map with your site. That's shown with the red pin here. Now what Tovi is doing is it's taking that location and then it's going out and it's finding these NOAA Integrated Surface Databases, or ISD, NOAA weather stations. Now there's 40,000 of them scattered all around the world in different locations. And what this software will do is it will find the 4 closest ones to your site. So no matter wherever your site is, based on your latitude and longitude, the map will show you 4 black pins, which are these sites. Now we also provide a secondary weather station database to integrate data with. This is the reanalysis interim data. Now these are panels, so if I zoom out here, and you can zoom out on your map, what Tovi does is it selects the 9 closest panels. These are 80 kilometer by 80 kilometer panels, which are model data for each of these panels based on weather stations, radio sondes, and a bunch of other type of weather data. And typically what you'll want to do is select 1 or 2 of these closest to your site, and perhaps 1 or 2 of these. Now for this, let's say for this example that we're working through, we're going to select 1 NOAA weather station data. I'm going to go ahead and select the one that's at the airport close by. Now, as this data gets imported into your station, each of these take about 5 to 10 minutes to load. The ERAI data can take anywhere to 15 to 20 minutes. Okay, so if you're going to select any of these, you're going to be held up a little bit through the next steps. So for this example, I would suggest you don't select any of these. When you do come through with your own data, you can select 1 or 2, or you can go ahead and select all of them. Okay, and when we're ready, we've gone through all 3 steps. We can go up to this top button and hit create. So now what starts to happen is all of that data is getting moved from your file locations on your desktop into the Tovi application software. And at the same time, that weather station data is starting to get pulled in already. So now what we're asked to do is create a timeline. And what Tovi is doing is it's looking at all the files that you've uploaded into your library. In our case, we just have these 2 files here. But if you have something like SmartFlux, you might have 365 files, basically 1 for every day of the year. And let's name our timeline. I'm going to call this 2013 data. You can call it whatever you'd like. And to add that to the timeline, you just click that plus button, and you can see the timeline gets highlighted, turned blue, and the file moves over to what's in the timeline. So I can add 1 or 2 files. I can add all the files. That's completely up to you as a researcher on what you want to explore. When you're ready, click on this create button. Now the next step we're going to do is start to do analysis of the data. Now I might want to do an analysis on a whole year of data. I might want to do an analysis on a small portion of data. Maybe I want to look at a week or just a month. Maybe I want to look at a season, or I want to look at 3 different months. So when everyone gets to this page, you can see the ability to create a new analysis. Okay. Now if we click there, again, you can come and click create many different analysis and time periods if you'd like. But let's go ahead and call this one Tovi practice. You can call it whatever you want. If you want, you can call it July, select July data. You can call it summer, and we can collect your summer data, things like that. So we'll call it the Tovi practice session. Now down here, you can see you have the ability to choose the timeline or the analysis you want to work in. So if I click here, I have the option to change the date. I'm going to go ahead and leave this set to January 1st, 2013. But I want to change the date for when this analysis ends. I want to have it end on December 31st. Hit select. Okay, so again, I can go in here and I can choose whatever time period I'd like to do an analysis on. Now what you'll notice is down here is whether your data has finished downloading from the weather station. Now if you selected the ERA you're going to see this downloading message for perhaps anywhere for 15, 20, 30 minutes, depending how long that takes. Because that data is actually stored on tapes, and they kind of have a robot that goes in there and is filling out those requests. So especially if there's a lot of people trying to get that data, then it will take some time. Now for me, you can see that it just finished. For those of you that haven't finished, you will see that this create button is disabled, okay? Once it finally downloads, you'll be able to take the next step. Now for those of you, you have an option here if you're following along. If you want to continue and you don't want to wait for that to download, you can simply uncheck that box. By unchecking that box, you can create and move on to setting up your site, but that data from the weather station will not be included. Again, you can always come back and download this data later, or if you're doing your own data, you can do that for real. So you can leave it checkmarked if you're ready, and we go ahead and click this create button. So now what it's doing is it's assimilating all that data, synchronizing up the weather data with your flux data, and putting that all together in a usable format so you can start to do some further analysis of the data. Now, now is a good time for those of you, while you're waiting for that to happen, if you have any questions so far, you can click on that questions icon and ask some questions. And the guys on the panel will be able to answer those while those are waiting. You can see mine is getting ready to load again as this progress bar starts to slow down and loading the external data now. We're getting ready to get to that next step. Now this process to get to this page depends a little bit on your computer and the processing power that you have. If you have an older computer, this process will take a little bit longer. Obviously, if you have a new computer and the processing power is fast, then you will get to this stage much quicker. So here are we on what we call the overview page, okay? And on this page, the first thing you're presented with is a coverage chart of your data. What we've done is group all the variables in your flux output files into groups, for example, a diagnostic group, a flux group, a meteorological group. And what this is showing is what percent of variables available over the time frame that you have here. So you can see some of them are almost 100% coverage over the year, and other ones are less than that. I can click into, for example, the meteorological group. When I click there, I'm now presented with all the variables that are within that group. For example, our air temperature, relative humidity. And you can see that some of these were collected almost year-round, and some of these other have some gaps. Above the chart, you can see some icons. For example, if I want to zoom in, I can click on that magnifying glass, and I can draw, click and drag on this chart here, and I can see the individual half-hour points. For example, if I want to find out when the power went out at my site, I can find out real quickly here that it happened on March 28th. Okay. Now the other things we can do in the software is you can see these tabs up at the top. If we move to the second tab, you'll see two dashboards available, one for the energy balance and one for the carbon cycle. Now, we're not going to go to those yet because we don't have a lot of our data analyzed, and so those are things that you will look at later in the process. Next, you can go to this data visualization tab. We have some different types of plots that you may want to run. For example, if you want to click on the fingerprints, you can do so, and you're brought to a screen where you can select variables. For example, I can select my evapotranspiration, and I can select, say, relative humidity. And what you can quickly see is a fingerprint plot that year of data, and that's a really very nice tool. each of these, you can save these figures by exporting them as well. Okay, now let's finally move towards this toolbox. Now, in the toolbox, we have two views. When you first come in here, we have all of the tools categorized by function. So we have some screening tools, we have some gap filling tools, etc. Now, a lot of people, especially if you're new to Eddy covariance, might not be sure where to start, what order to follow. So up here, you can see this blue ribbon in the right to the workflow view. Now, this is kind of the recommended workflow that you'll want to go through when you use Tovi. So the very first tool you'll be doing is quality screening, and then you move through all these tools, eventually getting to the energy balance, the carbon cycle, etc., and exporting your data at the end. Okay, so with that, I'm going to turn things over to Israel. For those of you that are ready, you can click on this quality screening icon to move forward and get ready for that.
Hey Dave, we've been getting some questions about bringing in external biomet data. Do you want to talk just a little bit about that?
Yes, there's, for those of you that may have processed your data in EddyPro, but did not do so with the biomet data, we actually have a document that describes how to do that. I can show some quick things to think about that'll be listed in that document. The first thing, an option you can do is to rerun EddyPro. And by this, using this step 3, when you use EddyPro, you can click this and use an external file. So if you have a biomet data file, this is probably the easiest way to do it, and simply load that file in here. Alternatively, what you can do is artificially modify your biomet file so it looks like the output file that EddyPro would provide. And you need to do some things like making sure you have positional qualifiers for your data sets. You need to make sure your timestamps are correct, including how the date is specified and how the time is specified. You need to make sure your file names are the same. So these are some things you can do. Now we have a document that's copy and pasted inside the chat window. If you click that, go ahead and download that. That's going to be really, really useful, very helpful for getting your data to be able to import that into Tovi. Okay, I'm going to switch controls over to my colleague Israel, and we can go from there.
Okay, Dave, thank you. Thanks for the introduction. I guess I wanted to start by saying thanks everyone for joining us again. These are these are very uncertain times, and I hope everyone and those you love are safe and healthy. And I hope you're finding strength and courage to get through this uncertain times. And we appreciate you joining us to learn about what data processing tools LI-COR has to offer. I'm going to switch a little bit from Tovi to talk to a slide presentation just to talk about some of the differences between the quality control things that happen inside EddyPro and what happen or what you'll do in Tovi. So let's start over there. Okay. So the key difference between the quality control that happens inside EddyPro and inside Tovi is EddyPro operates on the row fast or 10 hertz data or 20 hertz data. So that means it's looking at, for every half hour, it's looking at about several thousand, 18,000 records if you're doing 10 hertz or more to decide if each individual record should be included in the half-hourly results, in the averaged statistics or in the average covariance or in the flux, computed flux. So it has a lot more data that it's filtering through or screening through as it tries to compute flux. And EddyPro was designed to compute flux for all the half-hour as much as possible. So it will skip a few records, replace them if possible using interpolation, and still aims to produce a result for that half hour. It doesn't worry too much about what if those results are meaningful or realistic. It's just trying to optimize the input into the processing and give the flux value. So what EddyPro looks at to remove problematic values or records is, are there electronics issues, electronics related issues, such as resolution or spikes caused by electronics, or are there environmental issues? For example, do we have a sudden change in the reading of the instrument because a bug flew through the open path instrument, and that sudden spike, can we capture those from the statistics of the raw data? Also, EddyPro tries to look at the instrument function. Are there diagnostics from the gas analyzer or from the instruments that will help us to say this record should not be included in the averaging or not? Once we do these things, we remove those outliers, those problematic records, and EddyPro still processes a flux for that half hour, as long as the number of records and the number of removed records is less than 40%. So that's the maximum allowed. In contrast, for Tovi, for 1/2 hour, you have one value. And as a difference from EddyPro, when you filter data out in Tovi, it creates a gap in your data set. It's not going to be replaced until you do some gap filling or something along those lines. So unlike EddyPro, where it still tries to compute by removing some of the raw data, when you remove data from Tovi, you are creating a gap in your data set. So that's something to keep in mind. So what Tovi tries to help you with when you do QC is, are there things in the processing that came through that are not realistic? So did some computation go to some infinite value, and then the subsequent results make no sense or are outliers? Are there things that are outside the physical limits? Do we end up with temperatures in the negative kelvins or something like that? In addition, Tovi also looks at uses or quality flags that try to test whether the eddy covariance theoretical requirements are being met. So this is going to work in combination from what is done in Tovi, EddyPro, and what we can do in Tovi. So just to kind of reiterate, there is several statistical tests that are done in EddyPro. Spike elimination or spike count and removal is one of them. Dropouts, amplitude, resolutions I mentioned, absolute limits. So there's these are the settings in EddyPro that you can tweak around to make sure the data that goes into the calculation of a flux value is reasonably filtered and quality controlled. EddyPro not only uses that to filter data, but it also gives you several statistical results and or the test results. Some statistical tests that are done and gives you the results. In addition to these automated statistical tests, you can even add a custom variable or one of your data variables as a filter. So if you're looking at signal strength for the open path methane analyzer, or if you're looking at other flow rate, for example, and so on, you can use those in EddyPro to filter the raw 1020 hertz data out, so that your computed value has less of an uncertainty because you've already eliminated outliers and records that are not reasonable from the get-go. Another interesting feature that Dave mentioned about EddyPro 7 is the wind filter. So you can specify in the processing. This was not possible previously in the previous versions of EddyPro. You can now you can specify wind sectors where the calculation of the flux, if the wind, the instantaneous wind, each record has UVW and sonic temperature and so on, right? So EddyPro now calculates the wind direction for each record, and for each record, if that wind direction ends up in this, don't use this sector, then it doesn't get used in the averaging and the final flux. So there are things like that in EddyPro that allow us to remove several things that are going to be problematic for the flux computation and the resulting flux. So this is the question of what we get frequently is, if EddyPro is doing all of these things, why do we need to do quality control again in Tovi? And the answer is, while EddyPro tries to do automated statistical tests, try to detect these outliers and problems, it's not always possible to remove everything that is problematic or not realistic or those kinds of things in EddyPro in an automated fashion. So the next stage is to use scientific judgment and scientific tests and thresholds to filter data out. So the whole process is more about reducing the uncertainty or reducing the records with the largest uncertainty so that you end up minimizing the uncertainty of the flux or the total carbon budget you're after, or the total water loss or evapotranspiration for that ecosystem. It's about reducing the uncertainty. Even after we go through several QC options, and we'll see this, it's not going to be exact, but Tovi is going to give you some tools that you can use that may be, that give you different options. So what are these different options that we have in Tovi? It starts with simple thresholds or data range. That's the first one. You just set the limits for every variable. You can set limits and say, okay, if temperature is below -25 degrees Celsius, I don't expect, my site never saw those kinds of temperatures, so it should not be in my data. So you could set limits like that. If you have some knowledge about the site, other parameters that inform your decision, you can use data ranges like that. Some physical things cannot be, for example, CO2 concentration cannot be negative. It makes no sense. That probably indicates a problem in a gas analyzer. Too drifty or water got in and something along those lines. So you can say some things are physically bound and I should limit those to those physical bounds. Another thing you can do in Tovi, we will see this, is Tovi will give you the diurnal patterns, the daily patterns from morning to evening or from midnight to midnight. And those could be helpful in trying to decide or to inform your decision about what is a reasonable limit, what is a reasonable range for my data. The other is with experience. If you've been doing this for a few years, generally, if net radiation is 400 watts per meter square. That's the incoming, that's the available energy. It has to split between H and LE. And those kinds of information will tell you what should be the sensibility. Can it be, 800 when net radiation is 400 and so on. So you can use the relationship between the two and your experience with fluxes in general to set the limits. So that's something you can do for fluxes or any variable that gets imported in Tovi. There is another tool called date exclusion. This is simply, if you had some event going on at the site, some maintenance or some, for example, if you're at a farm site, they were spraying pesticides for the 2 days. So you want to select those 2 days out of the analysis because it may affect the results. So you can just select that period and it will be filtered out. The next one is Smart Y. The Smart Y range is an option to use the interquantile range, sort of a statistical test where you try to guess, or well, not guess, but try to see where most of the data values are, and you eliminate anything that's very far from where most of the data is. So you look at the spread in the data, and you find the values that are 10 times the LI-COR, which means they are huge outliers, and that does a nice job when you have spikes in the data in the computed flux or other values. Smart Y range does a good job. And the other option for variables is to use other variables. For example, for FCO2 flux, maybe you'll use the signal strength from the CO2 analyzer, the LI-7200 or LI-7500, and try to use that as a way to filter the FCO2 flux. What are the other options that are specific to fluxes? That's the main thing that we're after, but we have all these other variables that are also helpful. So when you're dealing with fluxes, in addition to all the tools I mentioned in the previous slide, we have quality flux computed by EddyPro, like the Folken flux that we'll talk about a little bit, the U-star flux, the gap filling flux, and the footprint flux. So I will talk about the Folken and U-star flags in the next couple of slides, and then next week we'll talk about gap filling and footprint tool and how you can use those for quality control. The Folken flags are computed by EddyPro, and this has been in EddyPro since I think version 2 or 3. But there's more coming in the EddyPro 7. There's more statistical tests and quality control indicators that are produced and that will come in the next iterations of EddyPro and Tovi. But in reality, what is the Folken flag? What do we mean by that? It's from the paper by Matthias Moder and Folken, Thomas Folken from 2004. They're essentially asking two questions. Do we have steady state conditions? And do we have well-developed turbulence? So they're asking how well each record, each half-hour data meets those two conditions. These are the conditions required for eddy covariance. For the eddy covariance method to be applicable, reliable, these two conditions have to be met. So you look at the steady state parameter and the integral turbulence characteristics, which also tells you about, do we have well-developed turbulence or not? So by looking at those, they assign a quality level to each data, to each half hour. So if it gets 0, that means it's high quality. So it's very likely that it meets both criteria and it meets it well without too much of a question. 1 means it's in the middle. So it's moderate quality. We would like it to be towards the high, but it's not quite. But it's not bad that we would say it's low quality. And 2 means it's low quality. That means it is it's not meeting the criteria for the measurement. So in general, 2 would be discarded. 0 and 1 would be included for budgets and analysis. 0 would be the best data to use for functional relationship or modeling the performance of the ecosystem. But if you say, I only want to keep records or fluxes that have 0 and 1 and exclude records that have the quality indicator 2, that means you're creating gaps in your data, and then you have to find a way to recover from those gaps by gap filling. Okay, so if we're using the Folken test to develop or to test for well-developed turbulence, why do we do friction velocity or U-star threshold or the U-star test? The debate in the scientific community continues about these things, but it is believed that the Folken test doesn't capture stable stratification, for example, nighttime, very well. So there's an alternative way to assess low turbulence conditions, and that's where the friction velocity comes in. And the question there is, if there's well-developed turbulence, then the flux, the biological flux, the nighttime respiration should not have sensitivity to friction velocity. If it has, it is an artifact. So that's the assumption. So the test is to try and see if you can find that sensitivity and at which point that sensitivity drops. So I took this from Abene et al. 2012 book. I forgot to add the year, sorry. But the plot is showing U star and flux, nighttime flux. So in theory, the biological flux does not depend on the friction velocity. So you will see this yellow pattern where it's relatively consistent across U star regimes. But in reality, what you see is for nighttime fluxes, you will see a very tight correlation between U star and flux values. They kind of increase together to a certain critical value of U star, and after that, the slope changes significantly. So the U star threshold detection is trying to find that critical slope, critical point in U star, at which point the dependence or the sensitivity of the flux to U star seem to go away. And by what that means is that U star, any flux below the U star, the critical U star value, is an artifact of the measurement. So that would be discarded. Again, this is something you will have to run on your data set, and we will look at it and apply it to your data. So as opposed to what I mentioned earlier in EddyPro versus Tovi, in EddyPro tries to, based on the available row record, try to estimate, do statistical test, and then eliminate records. You have some control there. You can tweak things, but it's still with the aim of producing a reliable flux result. With Tovi, you have control, but the result will be removing data from your data set. So you go in with Tovi with a much more, with a higher sense of responsibility, if I can say that, because you will be responsible for the decision you make about each record. And so let's go ahead and switch over to Tovi and try it. But before we do, I just wanted to give you a snapshot of what we're going to do. So we've talked about the different options. In these steps, what we're going to do is set the data range for H, LE, and FCO2 as shown here. And the quality flag, the Folken flag, we're going to use 0 and 1 as I discussed. And we're going to discard two quality flag 2 values. We're going to add flow rate and RSSI for the FCO2, use them as a dependency. And let's see here, and then we're going to do the smart Y range on the storage term for CO2. And we're going to run, we'll run the USTAR tool on FCO2 and apply it as well in the QC. So I'm going to stop sharing here for a second and switch over to Tovi. So can you see my screen now? Okay. What I have here is the quality screening tool. So I just, you can click here and go to quality screening, and it looks like this. So as Dave mentioned, the data is organized into groups. We're looking at the diagnostic group. So if you click to the fluxes, it will switch over to fluxes, and you'll see the variables starting with sensible heat, storage term for sensible heat, latent heat, storage term for latent heat, evapotranspiration, CO2 flux, storage term for CO2. We don't have a methane data for this data set, momentum flux, and friction velocity. So these are the variables that are in the flux category. So we're going to start looking at the time series of sensible heat and other fluxes here, and using that to do quality control. On the right side, what you see is the diurnal plot of sensible heat. Right now, it does not show a good pattern because we've got a lot of outliers that we need to remove. So the first thing to do is to kind of get familiar with the layout here. You got your time series, the diagonal plot. You got some zoom in, zoom out tools. You have an expand option here to look at things a bit more close. This right here is the date exclusion tool that I mentioned. So if you click on that and draw, it will remove data for that period. You can save this plot if you want to share it with someone or use it for later analysis. And this is adding to the notebook or to the process log. In addition to that, you'll see on the time series, you have the data and then these red lines. The red lines are the minimum and maximum thresholds that are being used currently. So right now, we are way outside where most of the data is because we just entered in this raw data stage. And it's showing us everything that's in the data with all the outliers and with all the questionable records. We can move these lines. You can drag it and move them, and it will move the threshold up and down, and it will also mark or set variables outside, records outside that threshold as ready to be removed. So a point turns yellow. And here in the legend, you can see how many points there are, how many of them are good, how many are missing, how many were excluded because of the data range, or any other of the tools that we discussed. So I'm not going to play around too much with the lines. I'm just going to kind of move them close a little bit. And then I'm going to go over here to where it says the y-axis options. These are, there are three things here. The first one is the data range. This is the tool I mentioned earlier, that this is where we set the limits or what the minimum for this variable should be. So I'm going to set here -200 for the minimum sensible heat and 800 for the maximum. So that moves the lines subsequently, and you can see where the lines are much closer to where the data is. There's a few outliers here at about 1% right now, and a couple of points above the maximum threshold. In addition to the data range, you have a couple of other options. These are setting the limits on the y-axis and how much zooming in and out you can do. So you can set the y. Right now, it's going all the way to where the data is, but including the outliers. So if we want to zoom in, we can set something like -1000 here, and about let's see, 1200 at the top. So now it zooms in the whole plot, and we can see the data much more visibly and clearly. So these are the the data options here under this y-axis options. The next tool icon is the quality flags. So this right now only has the Folken flags. So we're just at the first stage right after import. And you can see the maximum value is 2, the minimum is 0. As we discussed, we're going to use records that have 0 and 1. So that means we will move from the right to left to essentially include only 0 and 1. And you can see as soon as I did that, a lot of points turned yellow in the data or in the plot. And we are up to 10% of the data that's deemed bad by just these couple of steps that we just did. And if you want the detail, you can see in the legend, by using the data range, we eliminated about 1% of the data, but by using the Folken flag, we eliminated about 9% of the data. So that's how we got to 10% eliminated. We still have about 74%, so that's good. Next step would be to look at, let's see here. I'm gonna go back to the standard view here. So now that we've eliminated some of those outliers and kind of zoomed in on the data, you start to see the pattern of, what you'd expect. The outliers are still there in kind of faded one, but this is where most of the data is. And you can see it here. It's got high around midday, as you'd expect. Sensible heat is the highest around midday and then falls back to 0 in the evening. Okay, I think that's what we will do for sensible heat. So let's move on. I am going to move a little bit quicker now because the process is the same. You decide which variables you're going to look at, and you apply the filtering criteria that you want to apply to those variables. So for latent heat, again, I'm going to start with quality flags. We know we're not going to include anything that has a quality flag of 2, so that already removes quite a bit, about 12%. And then we are going to limit this to -50 to about, right where it is, or we can say 800 just to be consistent, watts per meter square. We can set the limits here so we can see the line where it is. And -100. So just so we have, -100. Just so we have the visibility of the data in a nice form. And, sensible heat shows a nice pattern here in the diurnal pattern. So we're moving on to FCO2. Again, FCO2, we're going to say goes from -50 to +50. Why do we choose these numbers? Why did I choose these numbers? Well, my colleague James Capelan, the eddy covariance expert, tells me from his literature review, usually CO2 flux rarely goes, I shouldn't say never, rarely goes below -50 micromoles per second per square meter. Even when you're looking at very active cornfield or something like that. And on the other side, on the flip side of respiration, it's quite uncommon to see respiration higher than 50. So I'm using his judgment and putting those numbers in. If you've seen things much narrower, you can use that, but it's you can start with a wider value and kind of allow the other filtering tools to take care of the rest. So right now we have removed very little because of the data range. Only 23 records, that's 0.1%. Let's zoom in on the data a little bit. Let's say we go to -75 and about 175 on top. So now we see where the data is. You start to see diurnal patterns. This is, I should mention, this data, as Dave mentioned, is from our research station. So it's just a lawn. And so we don't expect it to be super active, but there's pattern that you start to see now. Midday goes down, so that's the uptick, and then goes a little bit 0 or above during nighttime. Next step is the quality flag. So we're going to say only zeros and ones, and that's going to take out quite a bit of points. We're about 8% marked as bad because of the couple of steps that we did. So the storage term for CO2, this is a single point storage calculation that EddyPro does. It's not from profile measurement, but we will use that to compute NEE, and NEE is what's used in the USTAR threshold detection and other tools. So for the storage term that you see here, what you see right now is just a flat line because we have a couple, 4 outliers that are way outside the normal range or way outside where most of the data is. And so the smart Y range, that I mentioned, the one that looks at the I-COR and how far points are from that I-COR, is a great one to use here, because with just one click, it can remove those big outliers and kind of zoom in on the data and set the thresholds to a much more reasonable value. So this is plus or minus 2.2 for the storage term. So, you know, substantial number. So we'll go ahead and use that. That's for the storage term. Now, we've done many of the things that I mentioned. One thing I want to move on to is the dependency view, using the dependency view or using other variables to filter out the main flux or other variable that you're interested in. So if you click on dependency view, Tovi switches to a different view for your data. And here it just says, okay, you got to pick a primary variable. We're going to do FCO2 as I mentioned. And when we say FCO2, it shows us, okay, here's FCO2. And here are the variables that it depends on. The variance of CO2, for example. And again, we see a flat line. So we can go ahead and filter that using the smart Y. That's because of the outliers that were there. Okay. The variance of H2O. These are already default dependencies added. The assumption being if the variance of CO2 is an outlier or questionable, then the computed flux from that variance or from that half hour should be questionable as well. Because the CO2 and H2O gas analyzers are the same, are one gas analyzer, typically, you know, from the LI-COR 7200 or a LI-COR 7500A RSDS. So the assumption is if water is also questionable, then the CO2 is most likely questionable. So you can decide to keep those dependencies, or you can remove those dependencies. So you can click on this red button here. For example, if I'm already looking at the variance of water, I don't want to worry too much about the, if I'm looking at the variance of CO2 for CO2 flux, I don't want to look at the variance of water, so we can remove that. The next step is the variance of, or the next dependency is the variance of vertical wind speed, which is, you know, a factor in CO2 flux, and sonic temperature. This one I'm going to remove. Okay, so right now we only have variance of CO2 and variance of vertical wind speed that are used to filter FCO2 flux. So by filtering using the smart Y range on the variance of CO2, have I moved anything? Yes, I have moved about 595 records. Now, if you're happy with these two variables and that's all you want FCO2 to be filtered with, that's fine. But if you wanted to add, as I mentioned in my presentation, flow rate and signal strength, you can click here, add dependency, this green button over here, and choose that variable. Let's start with RSSI. RSSI is a signal strength indicator. It's not an absolute value, or it's not an absolute indicator, meaning when it's below X number, it doesn't necessarily mean the flux is bad, but you have to look at with the trend in the data. So if we look at here, the trend in the data says sometimes it goes below 60, which I would find a bit surprising, but okay, it's 60, but it's 60 consistently for the most part of the year. And except for this section here where it's below 30. So signal strength changes with cleanliness of the instrument, and the threshold you use should go with the trend. And the trend here is anything above 60 is kind of typical. Anything down here is problematic. So we can use this red slider and move the line closer where, you know, about 50 or so. So we remove all these points that have very low signal strength. So that probably means there was an instrument issue, maybe like water got in or something like that. And so we've removed a few days because of that process right there. So right now we've created major gaps in our data. We started about, let me see here. Yeah, about a few records missing, but by the steps that we've done, we've removed a whole lot more. So we're creating more gaps in our data set. Let's add one more dependency and we'll stop. The flow rate. The flow rate is, it's not necessarily, something that's going to be something that's going to have good fidelity and to do filtering. But if the flow rate is not correct, then the flux is probably going to be significantly underestimated. If you don't have flow, or if you're not at the right flow, then the flux is going to be significantly underestimated. Hopefully, if the flow is fluctuating around the set value, then the dampening caused would be corrected in spectral correction. But if you have, for example, periods where the flow is 0, then that's going to be a significant problem. So right now we can't really see the pattern flow because of a few outliers. So let's go ahead and just use Smart Y so we can get in and close, and the flow looks fairly consistent with a few outliers, and the major ones are removed, and I'm happy with that. So we've done a bit more for FCO2 because usually, the carbon flux is what we're after and the water flux. We've done sensible heat. I'm going to go back to the group view so we can look at the different groups. Sensible heat we've done, latent heat we've done, and the storage term we've done QC. So at this point, we've set the data, or we've set the settings for what Tovi should remove and what Tovi should keep. So if we go back to fluxes, Tovi still shows us what we did moments before with all the settings saved. Until we say we're done with the QC process, the data doesn't actually get removed. When we say done with the QC process, Tovi actually sends the data with the settings back to the backend. The processing in the backend says, okay, these records need to be excluded from the analysis. So we have what we need. Let's take a quick look at other variables, for example, net radiation and so on that we will use later. So this is net radiation. It looks very nice. The diurnal pattern looks very good. This is PAR or PPFD. Again, the diurnal pattern looks very good. This is shortwave incoming or global radiation. Looks very good. We could look at the other groups as well. And just to do a quick check, this is air temperature, looks very good, reasonable patterns on pressure, relative humidity, VPD. We have some gaps, but overall reasonable. CO2 mixing ratio looks a little bit flat, so let's filter that out using the Smart Y. Okay, so we are at a point where I feel we've done enough quick things to show you the different tools that are available in Tovi. And I want to switch over now to doing U-star filtering. Unless there are questions that you want me to talk about, or okay. Okay, so this is the U-star threshold detection. Again, this is under Toolbox, U-star threshold detection, using the MPT approach, moving point test. And here, like I said, it's trying to find where that which critical U-star threshold value is where that decoupling of the sensitivity of flux to U-star happens. So I'm going to run this. Let's see, this is fine. I've done a little bit of analysis here to filter the data and do storage correction. So it's now called NEE. and then also gap filled the air temperature and shortwave incoming, so that we go into this tool with a full data set, and cleaned as much as possible. We'll talk about gap filling, biomed variables probably next time in the next session. Here, the settings for the U-star threshold are pretty simple. You have the input variables, and then the bootstrap temperature classes and U-star classes. And what this is trying to do is trying to subset the data into different U-star classes and temperature classes, and trying to find that detection, or try to detect that threshold where that sensitivity goes away. And because if U-star could increase with temperature, or other environmental factors, which could also increase the biological flux. So you want to look at the data in narrow temperature ranges where the temperature increase is not the one that's driving the sensitivity. So you want to subset the data and look at it in different bins. So we can start with 7 bins and run this, and it will subset the data, try to find different U-star thresholds. You see that it does this by season, because the sensitivity changes from season to season. You can see the seasonal values here: 0.2 for the winter, 0.218 for the spring, and 0.15 for the summer, 0.18. If this seems a little bit high, or you want to change something, you can go back and change the variables, or change the settings. I want to do maybe 10 temperature classes. So we narrow the temperature ranges. So the more temperature classes, the narrower the temperature range it's looking at. We may get some improvement or not. You can play around for your data to see what happens. So things look a little different. We went down from 0.24 to 0.23. So this is the seasonal results. So winter, summer, fall, and spring. And this is the yearly result. So the tool is going to pick the most conservative approach out of the different U-star thresholds that it finds. So this one will end up being the value that's going to be used for the entire year. Here's another result plot here, which is similar to that plot that I showed in the presentation. This is the flux versus U-star, normalized flux versus U-star. And again, it's trying to estimate, okay, do we see a distinct change in slope? And it seems so, right? There's the slope for this one with the uncertainty in that. And then there's the slope for the values after the threshold, we know. And we see that it's not a very clean cut. I mean, it's visible, you can see it, but it's not as clean cut, because, for example, this period here, October, November, December shows flattening here as well. So you got to look at the data to see if this is an applicable value for your site. So you can go ahead and say done U-star threshold detection at this point, and it asks you if you want to save it or if you want to tag it with a specific name. And once it's when you click done, it's saving, it's actually applying that result and saving the data with the appropriate U-star result. At this point, we have the result for U-star, and we can go into the quality control tool again and see if we want to apply the U-star filter or not apply, and see how much that affects our fluxes. So I'm going to go back to quality control now. Go to FCO2. In theory, or NEE, in theory, the U-star threshold is mainly for FCO2 flux, but there's still debate whether it should apply for other fluxes. Tovi allows you to apply it, but let me expand this a little bit so we see. This is NEE. So right now we have good about 11,200 points. out of the 17,519 that we started with. So if I go to quality flags, right, this here, I have this MPT U-star threshold flagging. So we have the results from the U-star that we can apply. And the application is as simple as checking this checkbox, apply or don't apply. The moment I apply, however, you see where the data values that are excluded are significant. So we removed about 23.58%, about 4,131 records. So the question then is, okay, we're down to 40% good data. There may be more quality control that you do based on footprint or something along those lines. Is this the right approach? Is the 0.233 U-star value, is that too much? Is it removing too much data? What can we do? This is where you go back to your ecosystem knowledge and experience and say, well, is stable stratification really a major issue for me when I'm working on a lone site, short canopy, or is it more a problem for tall canopies or ecosystems like forests and so on? This is where you go back and say, okay, how much uncertainty are we causing by removing 23% of the data using the U-star tool? Have we captured most of this in the Folken flag, or can we use a lower U-star threshold? Well, maybe we can. We can use another method to detect that U-star threshold. This is called the CPD, the change point detection. So maybe we can go to that and see what that allows us to do. Maybe it will give us a similar value or a higher value or a lower value. We can see that. Well, how is this different from that? The first one that we used. You can look at this acknowledgement here to know where the science behind the tool is and what paper it's based on and who helped us implement the coding and the settings and so on. So this is based on Barr et al. From 2013. You can see all the different authors that are included in that paper. And we got help from Peter Isaac, the data manager for OSFLEX in Australia, and one of his colleagues, Ian McHugh. Ian McHugh actually wrote the code, and Peter helped with that code as well. So we're using that tool. So maybe this will give you a better results for the U-star value that would still allow you to do the test for well-developed turbulence and but not remove 24%. So these are the different options, and that's all I had. At this point, you can apply and rerun this and go back and filter, and then whatever you decide you'll have removed, maybe 20-30% of the data you started with, at which point you got major gaps in your data that you need to think about how to fill the gaps. Now, in general, it's not always necessary to fill gaps. Gap filling is useful if you're trying to create yearly budgets, annual sums, or monthly sums, and so on. But if you're looking at more functional relationship between, for example, water loss and temperature, or water loss and treatment, it may not be necessary to gap fill the data. So that's all I have, Abby.
Okay. Hey, Israel, we had someone ask about the _1_1_1 after the variables. Can you talk a little bit about how these are positional qualifiers?
Sure. So this came from Ameriflux, FluxNet networks, and ICOS. So to try and identify different sensors at an EC site, they use this HVR notation: horizontal, vertical, and repetition indicators. So the H, V, and R are indices that indicate where the location of a sensor might be. So sensor location 1 horizontal and 1 vertical could be about where the gas analyzers are. Sensor location 2 horizontal and vertical 1 could be maybe a meter or 50 centimeters removed from where the first location is. So each variable, especially the biomet variables where you might have multiple sensors of the same type, will have these qualifiers so that when you're looking at the data, you can identify which one is closer to the site, which one is closer to the EC measurements, which one is in the ground, which one is deeper in the ground, for example, for some soil sensors. And you can use that nomenclature or identifier. If you need more information, I think the FluxNet website has a detailed guide on how to do this. They call it the BADM, Biological Ancillary Data Management, I believe. Oh no, Disturbance Management. So it's a way to include, in addition to these horizontal positional qualifiers, it's a way to include additional information about the site and the sensors. Actually, I was thinking, there was a question while Dave was talking, there was a question about how about including weather data or sensor data from another EC system nearby and so on. If you have a couple of EC systems in close by and you don't want to use the NOAA weather station data, you'd rather use the one that's maybe a few hundred meters away. The positional qualifiers is another way you can import that data. You can include the two EC system data into your biomet and give it a unique positional qualifier. That way it gets brought in with the biomet data, and you can use it as a way to gap fill the drivers and the fluxes.
Okay. So that concludes sort of our presentation, but we're going to stick around and continue to answer questions. So keep sending those in. But I just wanted to remind everybody to join us next week for session 2, and we're going to talk more on gap filling and footprint modeling. Same date, same time. We'll all be back here. And then if you haven't already, I'd encourage you to go to our website and download your free trial of Tovi. You'll also see on the website, we have a library of tutorial videos that you can watch, and it digs into a lot of those tools that Israel and Dave showed today. So that's available for you as well. So yeah, keep sending your questions in. We'll keep typing answers. But Israel, Dave, James, if there's any you want to answer live and have a discussion on, feel free to chat.